Hi, in this lecture, the second part of the amplitude modulation methods is introduced. Here is the outline of this lecture. As a background, which will be useful for our analysis, low-pass representation of a bandpass signal is first given. Then the last two amplitude modulation methods, namely single sideband and vestigial sideband AM, are discussed. Finally, the concept of signal multiplexing, in particular frequency division multiplexing, will be briefly presented. By this slide, we will try to develop low-pass representation of a bandpass signal, shown in the figure. The formal definition is given here. A bandpass signal is a signal such that its Fourier transform is non-zero for frequencies in a usually small neighborhood of some high frequency, like f0. Note that the bandwidth of the bandpass signal is 2W, and W is much less than f0. Let us now see how the low-pass representation is obtained step by step. The spectrum of the bandpass signal, called x of f, is illustrated at the top of the figure. By multiplying the unit step spectrum, the right half of xf with a doublet amplitude is obtained. The resulting spectrum is denoted by z of f. Finally, shifting zf to the left by f0, the low-pass representation called x sub L of f is generated. The time domain representation of this signal can be also written in terms of z of t. In next several slides, various forms of the low-pass representations will be developed rigorously. Let us start developing the Fourier transform of the signal function. Denote this transform by S of f. By using the signal function, the unit step function is expressed here. The derivative of the both sides is taken. Then the Fourier transform are given. Consequently, the Fourier transform of the signal function is found. Now, by employing this transform, we will try to develop the Fourier transform of the unit step function. Recall the expression of unit step function in terms of signal. The Fourier transform of the both sides are taken. Finally, by substituting the S of f just derived, the Fourier transform of the unit step function is given. Now recall the Fourier transform of the unit step function. By the duality property of the Fourier transform, then through the scaling property, the unit step function, whose independent variable is frequency, can be introduced together with its time domain representation. Now remember the function z of f we have given in one of the previous slides. Through the inverse Fourier transform, the time domain function z of t is developed. By arranging the expression, z of t can be written in terms of x of t and x cap of t. Here, x cap of t is actually a special transform, called as Hilbert transform. Let us now evaluate what the Hilbert transform does in the frequency domain. For this evaluation, we require to find the Fourier transform of 1 over pi t. Let us first remember the Fourier transform of signal function. By the duality property, then through the scaling property, the Fourier transform of 1 over pi t is given. Consequently, the Fourier transform of x cap of t is introduced. We can express this transform in various forms. This can be briefly clarified. The Hilbert transform causes minus pi over t phase shift for positive frequencies and pi over 2 shift for negative frequencies. Let us now recall the signal x sub L of t, which denotes the low-pass representation of the bandpass signal x of t. This signal has its real and imaginary parts, where xc of t denotes the in-phase component and xs of t is the quadrature component. Now let us multiply the expression we have initially given by e to the j 2 pi f0 t. Then, after some easy steps, the bandpass signal x of t and its Hilbert transform can be finally introduced in terms of the in-phase and quadrature components. Similarly, the in-phase and quadrature components can be expressed in terms of x of t and its Hilbert transform. Alternatively, the bandpass signal x of t can be written in the following form, where v of t and theta of t are called as the envelope and the phase of the signal, and given by. It is important to notice that this expression is useful for the demodulation of the amplitude and frequency modulation methods. Similarly, the low-pass representation is also expressed in the following polar form by using the in-phase and quadrature components. In the double sideband suppressed carrier and conventional AM, the modulated signal requires a channel bandwidth of 2W, where W is the bandwidth of the baseband signal. However, either lower or upper sideband includes all frequency components in the message signal, and transmission of either sideband is sufficient to reconstruct the message signal M of t at the receiver. The resulting signal transmission is the single sideband amplitude modulation. Thus, we reduce the bandwidth requirement for the transmission. The block diagram for the generation of single sideband AM signal is shown. Mathematically, the generation of the signal is given in the equation. By the minus sign in the equation, the upper single sideband AM signal is generated. The plus sign corresponds to the single sideband AM signal. Let us investigate the equation for the upper and lower sideband in detail. Here is the equation for the generation of upper single sideband signal. The Fourier transform of both sides are taken. As we have already introduced, the upper sideband covers the frequencies either greater than the carrier frequency fc or less than minus fc. From the Fourier transform expression, this frequency range can be easily justified for the generation of the signal. Similarly, the equation for the lower single sideband AM signal is given here. Its Fourier transform is taken. We know that the lower sideband covers the spectrum ranging from -Fc to Fc. From the Fourier transform expression, this frequency range can be also easily justified for the generation of the lower single sideband signal. In order to physically generate the single sideband signals, there are some alternative methods, one of which is illustrated in the figure. In this method, a double sideband signal is generated, as we have already discussed. Then the generated signal is passed through a filter to obtain one of the sidebands. In the figure, a high-pass filter is shown to extract the upper sideband signal. Similarly, a bandpass filter might be used for the lower sideband. An example is given here. The message signal is cosine 2 pi fmt. We need to determine the two possible single sideband AM signals. Let us start with deriving the Hilbert transform of the message signal. Its Fourier transform is given here. By employing the inverse Fourier, the Hilbert transform is introduced. By substituting the message signal and its Hilbert transform into the modulated signal expression, the upper and lower single sideband signals are obtained. By using the following trigonometric identity, the final forms of the modulated signal expressions are given. In the demodulation process, the received signal is first multiplied by a locally generated sinusoidal. Then, by employing the identities, the multiplied signal is rewritten. The resulting signal is then passed through an ideal low-pass filter to eliminate the double frequency components. By considering the carrier phase, the output signal can be updated. As you realize, for a successful demodulation, a phase coherence is required. For a coherent demodulation, the two phase terms, namely pi and the carrier phase pi c, should be equal, such that this allows a successful recovery of the message signal. This can be achieved by adding a carrier term into the transmitted signal. This signal is commonly known as pilot tone. At the receiver side, the added signal can be recovered by a narrowband filter and used in the demodulation. This operation makes the phase terms equal. Due to its spectral efficiency, the single sideband AM is very attractive for voice communications over telephone channels. By this slide, the Vestigial sideband AM is introduced. In the generation of single sideband AM signal, there is a sharp frequency response requirement on the sideband filter. This sharp frequency response requirement can be relaxed by allowing a vestige part. However, this causes an extra bandwidth requirement, which is about 1.25 of a sideband. The resulting signal is called as Vestigial sideband AM signal. The transmission of video signal in commercial television broadcasting is based on Vestigial sideband amplitude modulation. To generate a vestigial AM signal, we have to produce a double sideband AM signal and pass it through a sideband filter HF with a vestigial part. The time and frequency domain representations of this process is given here. Two example sideband filters are shown in the slide. The top filter is able to select upper sideband. Its vestige part is here, and the remaining part is used to select the upper sideband. The below filter is able to select lower sideband with its vestige and lower sideband parts. The demodulation involves two steps. In the first step, the received modulated signal is multiplied by a carrier signal. Then the resulting signal is passed through an ideal low-pass filter. Let us derive the signals rigorously. After the first step, the V of t is obtained. It can be introduced in the time and frequency domain. By substituting U of f, we obtain then double frequency components are eliminated by the low-pass filtering. Assume that a filter to select the upper sideband components is used. Then the second term in the resulting signal can be illustrated as follows. As you realize, in order to successfully recover the message signal, this term should be constant within the range from -W to W. A message signal is given in the example. We need to specify the frequency response characteristic of a vestigial sideband filter that allows the upper sideband and the first frequency component of the lower sideband. Let us first investigate the spectrum of the message signal. It is shown like this. We require to design a filter that allows the upper sideband and the first frequency component of the lower sideband. The designed sideband filter should satisfy the condition we have already given. Based on this condition, the filter is presented. The filter should have a unity gain in that frequency range. 0.5 gain at the carrier frequency Fc. 0.5 minus alpha gain at Fc minus 1. 0.5 plus alpha gain at Fc plus 1. Here alpha is an arbitrary constant less than 0.5. By this slide, we initiate our brief discussions on signal multiplexing. The process of combining a number of separate message signals for transmission over a common channel is called multiplexing. There are two commonly used methods for signal multiplexing. The first one is the time division multiplexing, which is usually employed in the transmission of digital information and will be discussed later. The second is the frequency division multiplexing, which can be used with either analog or digital signal transmission. We will focus on frequency division multiplexing in the next two slides. In the figure, a generic FDM-based system is illustrated. In the FDM, the message signals are separated in frequency by using different carrier frequencies. The low-pass and band-pass filters are also employed to specify and select the frequency components. FDM is widely used in radio and telephone communications. For example, in telephone communications, each voice message signal occupies a bandwidth of 3 kHz. The message signal is single sideband modulated for bandwidth efficiency. In the first level of multiplexing, 12 signals forming a group are combined and transmitted simultaneously. In the next level of FDM, a number of group channels are combined to form a supergroup channel, and the composite signal is transmitted. Higher order multiplexing is obtained by combining several supergroup channels. Thus, an FDM hierarchy is employed in telephone communication systems. This is the last slide of the amplitude modulation part.